Yes, I'm serious today. So for this integral, this integral is from 0 minus infinity to infinity, gamma of 1 plus ix, gamma, sorry, gamma of 1 minus ix dx. If any of you do not know what gamma function is, gamma is actually the real number expansion, or that's a complex number expansion of factorial function. Now, before we begin with the integral, we need to know some of the preliminary ideas or properties, which are like this. We basically need to know that gamma of n plus 1 is equals to n times gamma of n, and factorial equivalent of gamma will let you see why this works. Yeah, gamma of n is actually n minus 1 factorial, and you can see from there. And the next thing we need to know is gamma of n times gamma of 1 minus n is a uh, pretty non-obvious thing. That's pi over sine by n pi. So you need to know that as well. This can also help us derive what gamma of 1 by 2 is. Now you can check that. And the next thing we need to know is about sine of ix. The sine of ix, for this one, you can just go it this way. So sine of theta is actually e to the power I theta minus e to the power minus I theta by 2i. And to see why this works, you need to know the other formula again, which is e to the power I theta is cos theta plus I sin theta. And if you know this, we can just substitute the values over here from the formula, and to see how this works, to see why this formula is true. And now if you know this, we can just find out sine of ix. So do substitute ix in place of theta, and you will see that the following formula will be there. You will have I times e to the power x and minus e to the power minus x by 2. You will see that if you replace theta by ix, such formula will be there, and then this is I times sine h of x. Yeah, so you need to know this three formula to do this integral. So let's now begin. So now for gamma of 1 plus ix, we know that gamma of 1 plus n is just n gamma of n, so this will be ix gamma of ix. So it's actually iota will be more reasonable to pronounce than I. So it's gamma of 1 minus ix dx. Now we'll use the next property, that was gamma of n, gamma of 1 minus 1 n was pi by sine n pi. So if we use that, we will get this integral to be integral from negative infinity to infinity, ix times pi by sine n is ix, then pi dx. Now we will use the other formula that I told you earlier, that sine of I theta is just I times sine s theta. So that will lead us to integral from minus infinity to infinity, ix times pi by I times sine s of pi x dx. So I'm sorry if it's not clear. Okay. Now integral from minus infinity to infinity, this I will just cancel out, and pi x over sine h pi x is what remains with us, and dx. Now we'll use some high school ideas about integrals, that when we have sine such things in denominator, we can first break down into 2 sine pi x by 2, cos pi x by 2, and then divide numerator and denominator by cos square x by 2. That will give us sec square x by 2 in the numerator and tan x by 2 in denominator. And we can just take tan x by 2 as y, so make substitution that, and we will have sec square in the dy term, so that will work. Now we can do that. Negative infinity to infinity pi x, and we break down the denominator into 2 sine as pi x by 2, and then cos as pi x by 2, and then over here we have dx. Now we can divide numerator and denominator by cos x square x by 2, cos x square pi x by 2, and that will give us pi x by 2 here, tan x pi x by 2, and in the numerator we have sec x square pi x by 2, and then a dx over there. Now we can just let y as tan x pi x by 2. If we let y as tan x pi x by 2, we see that the derivative dy will just be sec x square pi x by 2, and then here pi by 2, and then dx. Okay, now we can see that sec x square pi x by 2 and then pi by 2 and then dx are all here, so that will be dy. And for the change of limits, we need to look at the exponential equivalent of tan x by 2. So we know tan x by 2, tan as theta is actually e to the power theta minus e to the power minus theta by e to the power theta plus e to the power minus theta. So this will be e to the power pi x by 2 minus e to the power minus pi x by 2 by e to the power pi x by 2 plus e to the power minus pi x by 2. So this will be it. And now when x goes to minus infinity, I'm sorry, pretty what just recently happened, is e plus e to the power minus pi x by 2. Okay, so now when x goes to negative infinity, these two terms will go to 0, and these two terms will be just equal. Yeah, since these are going to 0 and these are going to these will be equal, so you can just cancel them out, and negative 1 by 1 will be just negative 1. So from negative 1, and when x goes to infinity, these two terms will go to 0 and these are equal, and we have 1 by 1 over here, so that will be 1. And for this x, we can just change, we have tan x inverse y equals to pi x by 2 over there, and then x equals to 2 by pi tan x inverse y. So you can use this. Our x is 2 by pi tan x inverse y, and sec x square pi x by 2 pi by 2 dx is just dy, and the tan as pi x by 2 will be y. Okay, so now what you can do is we can just take the constants out. Integral from -1 to 1 tan x inverse y by y dy. Now we can use the series expansion of tan x inverse y. That will make our life easier since we just have y in the denominator. After that, we need to know first series expansion of 1 minus y x square, which we know is just a geometric series. So this will be 1 plus x square plus x4 to the power 4 plus x to the power 6, and so on. And now we know that its integral is just tan x inverse x. And over here we have x plus x cubed by 3 plus x to the power 5 by 5 plus x to the power 7 by 7, and so on. But we also need to have a constant over here, which is the constant of integration plus c. Okay, after this To get the value of plus c, we can just substitute x at 0. If we substitute x at 0, we know that tan inverse x is also equals to 1 by 2 ln of 1 plus x, 1 plus x by 1 minus x, and tan inverse 0 is just 1 by 2 ln of 1 by 1, so that's ln of 0, so it's 0. So tan inverse 0 is just 0, and over here we will have c plus all the terms will go to 0, so that implies c is also 0. So we have got the series for tan inverse x to be x plus x cubed by 3 plus x to the power 5 by 5 and so on. Now we can just erase this. And now we can finally write the series and do the integration and come up with the answer. We are very close to the solution. This is y plus y cubed by 3 plus y to the power 5 by 5 plus y to the power 7 by 7 and so on, divided by y dy, and 2 by pi integration from minus 1 to 1. This is 1 plus y square by 2 plus y to the power 4 by 5 plus y to the power 6 by 7 and so on, dy. Now to make this integration, we can just integrate it term by term, and that's also easy. Y plus it's fine, but it was 3 over here, not 2. Now it's fine. Y plus y cubed by 3 square plus y to the power 5 by 5 square plus y to the power 7 by 7 square and so on, and evaluate from minus 1 to 1. So if we evaluate that, so if we evaluate that, you can just do it. I just leave that for you. We get it to be 2 times 1 plus 1 by 3 square plus 1 by 5 square plus 1 by 7 square and so on. So that's 4 by pi times this series over here. Now to find the value of this series, to know how much it evaluates to, we can first begin with the other series of zeta of 2. We know that the other series zeta of 2 1 by 2 square plus 1 by 3, I'm being too fast, 1 by 3 square plus 1 by 4 square plus 1 by 5 square plus 1 by 6 square. This series evaluates to pi square by 6. Now we can just group the odd terms. We can just group the odd terms and the even terms. But in the even terms, we would want to take 1 by 4 common. If we take 1 by 4 common from the even terms, we will have 1 by 1 square over here. Here we will have 1 by 2 square. In 1 by 6 square, we will have 1 by 3 square. In 1 by 8 square, we will have 1 by 4 square, and so on, as pi square by 6. I guess that was 2, let's see, pi square by 6. Now this is the sum that we want. Let it be s, and we know that this is again the same sum, so it will be pi square by 6, and that's pi square by 6. So we get our required sum to be 3 by 4 times pi square by 6. So that will basically be pi square by 8. So the sum that we want, this sum is actually pi square by 8, and that is pi by 2. So we see that how neatly this evaluates to pi by 2, which is just sine inverse 1, which is just cos inverse 0 for principal value. So this integral evaluates to pi by 2, and hope you enjoyed this solution, and hope you also learned a lot of new ideas about evaluating an integral. And if you like it, do share with your friends. And yeah, thanks for watching. Wishing to see you in the next video. Look forward to seeing you again soon.